We're talking about free boundary value problems. One of a couple or three more advanced topics that we'll consider at the end of the term. The other one I was thinking of doing was reaction diffusion equations, and I'll show you how Turing instability can come out of those. Interesting topic in chemistry and mathematical biology, and then we'll see how the time goes. Things always take longer than I think they will. Okay, let me share the screen. I'll remind you where we were last time talking about the Stefan problem. I'll remind you of the formulation we got to, and then I'll start showing you some simplifications that you can make to the model that apply in other kind of free boundary problem cases, and also which will let us do some analytic work on these that'll show up on the next assignment. Okay, let me share, and let me minimize, exit full screen so I can see the Slack channel in case there's comments coming in that I should address. Okay, so this is where we got to last time. It was the 1D Stefan problem. So this is a problem we've posted in a bounded domain. I've got a temperature that's positive over here. This is above the melting temperature of water. And I've got the heat equation in the water. And of course, I would have had to have given initial conditions. I didn't think I talked about those last time, right? Then I've got this curve, S of t. Now this is not a given curve, right? This is a boundary. I mean, it's not really a boundary. Maybe I should call it an interface, because it's not at the edge of the domain. It's in the middle between water and ice. And this is to be determined as part of the problem. So that makes this a free, or sometimes free boundary value problems are intended to mean steady state. So maybe I should say moving boundary value problem. And these come up all the time in engineering and science questions. More advanced kind of thing, because you don't just have the simple equations and boundary conditions. You got this unknown interface to be determined. And of course, I would have had to have given initial conditions here in the ice region that were below freezing. And then you look at here and you go, well, I got parabolic problems on either side. So I'm going to need interface, or I'm going to need boundary conditions for them, one each. And I also need another condition to tell me how S moves. And so there is a explicit velocity condition given by the jump in the partial derivatives. This is notation for the derivative difference between the right and left sides, or left and right sides, I guess I should say. And this is saying, this was all scaled. We talked a little bit about that last time. So in the scaled format, this is saying, remember the derivatives of temperature give a heat flux. So this is saying the difference in heat flux on either side is causing the ice to melt or freeze. And so this interface is moving to the right or to the left, depending on the sign of this, this difference. Okay, well, there's one condition. And of course, the other conditions, I got two of them. On both sides, I'm at 0 temperature. I'm assuming that the freezing and melting is all happening at 0 temperature. Now, there you can get into more detail if you look at these things in the fine scale about solidification and melting. But this is a good approximation in a macroscopic scale. So this is a problem you can solve for, I'll say, u plus and minus of x and t, the two different functions, the ice temperature and the water temperature, and s of t. Now here's a subtlety, which I guess I haven't sort of stressed in the notes, and I'll have to come back to that, either in an assignment question where you can explicitly see this, or talking about this in a different free boundary value problem. But if you look at this, everything looks linear, okay, right? I've got this linear PDE for the temperatures. I've got these conditions that look linear at the boundary, but I'll say the influence of s of t on u plus and minus of x and t is nonlinear. So the whole problem is nonlinear because you have to solve these things together. Let me come back to that and reinforce that a little bit. It's nonlinear. And in fact, all free boundary value problems are nonlinear. So, okay, we've left the world of linear problems. You can't superimpose solutions in this sense. Okay, so I guess I want to come back and say a couple of things. I'm going to look at simpler versions of this model. So this one was model T for two-sided. Okay, we're going to look at a one-sided model and then a simplified one-sided model, which will end up being on an assignment question coming up. Oh, yeah, that's right. I wanted to come back and stress something. If you knew S of t, right, then I would have two separate linear problems to solve for the temperatures, right? Just with this simple boundary condition, right? That would all be linear, right? If S of t were known. You don't know S of t, right? And I guess I want to say the other way is there's no way to solve for u simply and then post-process S as the location where the temperatures are 0. So what I'm trying to say is there really is a full coupling between S and the temperatures on either side. This is not something you can split up into pieces. You've got to choke this all down at the same time. Okay. So let's look at some simplifications, right? I'll do 2 stages of simplification, ending up with something we can kind of sink our teeth into. Let's look at simplifications. Let me say it is consistent to make a one-sided problem. With U identically equal to 0 in the ice region. So we can go back up here. We can set U identically equal to 0 with initial conditions and give U is equal to 0 as the boundary condition. And then no matter what S of t does, I'm solving the heat equation with 0 conditions all around. And so I'm just going to get U identically equal to 0 in this region, right? Which means I can forget that side and I just have to look at this one-sided problem. So we can do that. So we'll have S of t we still won't know, but U will be identically 0 out here in the ice. So I don't have to solve for that part. I'm going to have the heat equation over here. I'm going to have U equals, okay, well, I'll have initial conditions here that are positive. I'll say bigger than or equal to 0, because to be consistent, they should be 0 at this point, right? And then on this boundary, I'm going to have U equals 0. There's only one U now, right? This is the water side temperature. And I will have ds by dt is minus du dx, right? Coming from the left-hand side, right? But there is only the left-hand side now, so I won't put that. That's just taking the du dx on the positive side is 0 in the same expression we had before. Okay, so it's a little bit subtle to remember all the details from last time, but remember we scaled the temperature so that we could have this expression here with easy units. Oh, and by the way, this is model, it was model T before, this is model 1 for one-sided. When we did the scaling to get this, we scaled to temperature, and there were a bunch of things that went into it, but one of which was the latent heat, right? So this is really measuring temperature in terms of latent heat units. And there was density and a bunch of other stuff as well. But in that scaling, there's many applications that you could look at where you will end up small in many cases. Okay, and you know what to do when you know that something is small is you call it epsilon times something, right? And you put that in the equations and you see if something sensible comes up. Now, we're doing something a little bit different than the asymptotic stuff that has come up in a number of the problems, especially the part B problems. We're not going to correct for the order epsilon terms we're going to say, hey, there's a dominant process that doesn't have epsilons in it. That makes sense. That's all we're going to care about. We're not going to worry about the correction in this. So if I do that, of course, well, I don't, I don't change this equation because I got epsilons on both sides. So I'm going to get VT is VXX. Right? Here I've got V identically equal to 0. Here I've got something interesting is going to come up. There's an epsilon that comes in. So that means that the free boundary moves slowly. If the temperature and its variations are small, right, then this free boundary moves slowly. Well, in fact, one of the things that in these problems we care about the most is where's the free boundary, right? Where's the ice, right? Is it, you know, frozen something we're interested in, right? And so let's scale time. So we capture this slow motion. So the time scale we should take is t divided by epsilon, right? If I'm moving at order epsilon speed, then I want to wait an order 1 over epsilon time to get somewhere, right? Okay, so I'm going to do that. And if I make that change of variables, I get epsilon v tau is vxx over here. And I get ds by d tau is minus dv dx. And I've still got v is equal to 0. This is all the conditions on the free boundary. Okay, so now I've got the boundary moving at the speed where something interesting can happen, right? But now I see that this means the temperature time scale it's quite fast, right? So it's going to reach a quasi-equilibrium in the time scale that this is moving at. So let me write out some things if you haven't seen this before. Basically, what I'm going to do is I'm going to cross this out, right? I've still got my boundary condition, which could depend on time, right? So that's something that I've got to keep in mind, right? But I'll just say at this time scale, this equation reaches a steady state. Well, okay. And this is called a quasi-steady. Okay, because it's only at this time scale that you're reaching a steady state, but this S is moving and this V is changing, and so this is also changing. Okay, so if I now change notation back to T, because I don't like writing taus, and maybe I should make a little bit of a comment about this. This is a very typical thing in applied math. And I think, you know, the branches of engineering that are close to applied math, you know, this kind of scaling technique is often used. And so you have, you know, T is scaled to be something. But everyone likes T for time, whether it's scaled or not. And so often after pages of, you know, t is transformed to tau, then you have the scaled equations in tau and you just write them back as t again. And you're supposed to remember that t is not the original t anymore, it's the scaled time. So here I'm going to have this boundary temperature. This is going to be given. I've got Vxx is equal to 0 in the region until I get to the free boundary, right? And then I'm going to have ds by dt is minus dv dx, right? And okay, so this is a model, right? This is, I called it E1, I can't remember why I called it E for epsilon. It's one-sided, but it's got this epsilon in it, right? And this one we can solve analytically. Right, S will vary with this VB, but at every time I've got this quasi-steady state. So all I know is that it's linear in here, right? With coefficients in the linear expression that vary in time. So this is VB of t times 1 minus x over s of t. Right? That's the linear function that goes from this value at x equals 0 to the value 0 at s of t. And so now if I want to look at dv by dx, well, it's a linear function, so this is just a constant. And ds by d tau, remember, is minus dv dx at x equals s, but remember this is just some constant, so this is vb of t over s. Right, and so let's notice this is just an ODE for s of t. If you had any kind of reasonable given function VB of t, you could and initial conditions for the interface, you could solve this because it's separable, right? I can look at that and go multiply through by s and dt and integrate both sides. And then, of course, you have to try and invert the function, but let's say you could do that. And remember, I said, even though everything in this problem looks linear, it isn't. I guess I had forgotten that I had this note in the notes. This is where you can see that the problem is nonlinear. So I'm showing you the nonlinearity in this simplest case, where you can do things analytically. But it's true for all the other more complicated problems, T and one up above. Okay, so this, I'll say we had 3 models, right? The original model and then 2 simplifications. So that all of these models can generalize to higher dimensions. So let's look at the two-dimensional, two-sided problem, right? I'll have water over here, and I'll have ice over here. I can't show time anymore because I'm using up my 2 dimensions for space. Right, I'm going to have the heat equation in 2D over here. I'm going to have the heat equation with the scaled thermal conductivity over here. I'm going to have an interface which has some sort of parameter on it. I'm going to have a normal direction, and the normal velocity of the interface is given by the jump in the normal derivatives. So you have a normal velocity given. Now, of course, the sort of the analysis of these problems, showing existence and uniqueness is not trivial, right? How have we made progress on existence and uniqueness? We found series solutions, and we've looked at some maximum principles or energy estimates and shown there can be only one solution, and we've got one with this series. That makes sense. The analysis of these things is more complicated. So that's something we won't do in Math400, but I think it's good to see these kind of problems which can come up in applications. There are some computational codes out there that can handle solidification problems, and now you know some of the ingredients that those would have. There's a question coming up. What is the S parameter in this thing? That's the parameterization of this curve, right? It's a curve in 2D, so I need a parameter to describe it, right? I could have just, a typical math thing is just, I could have just said, oh, it's gamma, and there's a normal velocity. So in this problem, and in what I'm going to show you later, okay, so this is, Math400 meets computational discussion. So we're not going to compute anything, but I can at least discuss things. So the way I've written this problem down makes you kind of think if you were going to compute, you would do something called tracking, right? So you would actually have a representation of this curve, and there would be points on the curve, and you would move those points with this normal velocity, and maybe solve these problems with a finite element method on either side in this moving domain. So that's what's known as a tracking method. Now, this isn't a computational course, so you don't need to know this. But what I'm going to show you next is a different formulation, which you have to get into if you want to consider solidification in a more general setting, and I'll show you why that's true. What I mind? Sorry, I'm going to have to wait for Maricela to put that in. Would you mind uploading computational examples? I'll show you a method that you can turn into a computational method for this problem. How about that? And there are reasons why you have to get away from tracking, right? In these solidification problems. But even when you can get away with this kind of interface representation, keeping track of the topology and moving the grids on either side to conform to this boundary is a pain. So what you want to do is to have a method which, instead of tracking that interface, just has a grid and works out basically when you should be ice and when you should be water, and that moves the interface at least approximately in the right way. And that's what's known as a capturing method. So I'm going to tell you about a formulation that's more like a capturing formulation, and why you're stuck with it in some cases, even if you're okay with tracking. So I'm moving on to the posted lecture notes for lecture number 20. We were finishing up the ones from lecture 19 up to this point. Let me say the Stefan problem, that's the one up there, emerges when solidification or melting, right? Just with the, for me, that's just a sign change, occurs due to boundary forcing. You know, it is a very simple example, okay? But you can see exactly here how the boundary forcing moves the ice interface around. That was the most reduced model, but highlights sort of the general thing that's happening. So now let's look at interior forcing. And I'll say things are actually quite different in this context, and you'll see that. Hopefully, I'll convince you that things are going to be quite different. So I'm gonna start with a domain that's all water, with U the temperature positive. Okay, so I'm going to have thermal diffusion, but now I'm going to have this volumetric source term. Now, okay, this volumetric source term, which I'm going to have be negative, right? So I'm cooling down the water. I'm trying to think of an example of how this could happen in water. You'd have to have water with some stuff in it that was having some sort of endothermic reaction, right, in the bulk. So it's a little bit artificial. Where where the phenomenon that I'm going to talk about does occur is in metal solidification in molds, or different things, and there that's at quite high temperature. There you can have radiative heating, which is a volumetric term, and of course you're radiating heat out. This F could be negative. Now in that case, this F is some nonlinear function of the temperature and all kinds of other things, and I'm just kind of putting it in the simplest format that I can think of. There's some given F of T, it's negative, you're cooling things down. So I'm gonna draw this picture of this domain. I'm gonna show some U of X and T plots as a function of X. T will be increasing, right? Because my F is negative, so I'm cooling things down, so the temperature is gonna go down, right? I'll have U is equal to 0 here, right? This is where things will start to freeze. And I'm gonna say that I'm gonna have insulated conditions on the two ends, right? So, okay, so here is my initial conditions, let's say. right? And now I'm going to cool it down. And at some point, right, as I keep cooling it down, let's suppose that this F is just, -1, right? So it doesn't depend on X and T. It's just uniformly cooling everything. Well, at some point, I will hit a 0 temperature, and it will happen here. And of course, I've got some diffusion going on. So, right, this is going to flatten out a little bit, but let's assume that that's not too significant. I'm going to have this temperature, right? So now I'm going to have a freezing. I'm going to start here. But if you, and I was trying to think of how this is obvious, but you don't form like a piece of pure ice right there. You just start to freeze it, right? Okay, and then let's look at a later time, right? I can use a different color. Here, I got this green one I don't use very much, right? Right? Now, I'm not going to get below 0 temperature, right? Because I have to cool down, I have to take heat away for it to freeze. So in fact, I'm going to get stuck at the 0 temperature, right? So I'm going to have some freezing starting here, and ice will form. But it won't be pure ice, right? There'll be a fraction of ice, right? Between 0 and 1. So this is going to be pure water. And this will be pure ice. And in this region, at some point, I'll have cooled it down enough, I will get pure ice. But before then, I'm going to have this region where I have a mixture of ice and water. And this is called a mushy region. It's a mix of ice and water. Okay. So there's no Stefan problem here anymore, right? Because there's no sharp interface between pure ice and pure water. There's this kind of thing in here which mixes things up. And let's look and see what's happening in there. Here's my thought experiment, right? There's a reason I'm a mathematician, which is because don't let me do any actual experiments, okay? But thought experiments I'm okay with. I can't break any equipment or leak out any expensive gases in the lab if I do a thought experiment. So here's my thought experiment. And it leads to a thermodynamic concept, which, let me say, thermodynamics was my weakest subject as an undergraduate. So you probably understand this better than I do. Okay, so in my thought experiment, I'm going to start with water, temperature positive, and I'm going to cool it uniformly. And I'm going to stir it so it is uniform behavior in space. Right? It's a stirred tank. I got a stirred tank with water that I'm cooling down. Okay, so what's going to happen? I want to look at what happens to the temperature as I remove heat. And I'll scale it to be at a unit rate. In time. So how is this going to look? Well, here I am. I'm starting at my my positive temperature, right? I'm doing all the scaling so that temperature is going to go down at a unit rate, right? So in time, right? So this is really time is going on here, but we're going to turn this into a quantity which you may have heard before in your thermodynamics classes, if you've had a thermodynamics class. And if you haven't, well, then you're more or less in my boat, right? It's going to cool down, right? It's going to cool down until you get to zero temperature, right? But when you get to zero temperature, it's not going to freeze completely, right? Instantaneously, because there's the latent heat, right? You have to take out all of that latent heat to freeze your bucket, your well-stirred bucket of water, right? So here we go. All right, here we go. I'm going to keep removing heat, and I'm going to stay at zero temperature. And here is where I'm going to have my ice form, right? Here is water out here, right? And then once I'm here, right there is where I don't have any water left. Oh, I got this backwards. Water is 0, ice is 1. Is that what I got? Yeah, okay, sorry. You know, it's a fraction of water or a fraction of ice. I got mixed up there. Okay, so here I started with no ice. Here I'm completely ice. And of course, once you're completely ice and you continue to remove heat, right, then the temperature will go negative, right? And in here, I've got the scaled latent heat. So there's all kinds of scaling going on where this is going to be 0.1 and these things will all have slope 1, okay? So now I want to encapsulate this idea, right? So somehow I have this idea that I've got some internal amount measure of heat, which doesn't correspond to the temperature because of this thing, right? Right? But should include, you know, the heat of melting and freezing, and that's called the enthalpy. So enthalpy, people out there, is this your friend? Enthalpy? It's not my friend, except in this particular application where I don't know what it means thermodynamically, but at least I understand this thing. No, yes? No, yes? Okay, Julie, I agree. Enthalpy is a vague acquaintance. Yeah, for me too. But in this context, hopefully I've made this clear, right? So heat flux into this thing, right, is changing the enthalpy, right? If you're out here and you add or remove heat, then you're changing the temperature. If you're at zero temperature and you're adding and removing heat when you aren't completely ice or water, then you're just moving the amount of ice or water back and forth, right? And if you're over here where you're completely ice, then adding and removing heat is just taking you back and forth here. So the enthalpy, so this is all scaled, right? The enthalpy is just U plus phi, right? So now we started off with this heat equation for the temperature in the water. When ice starts to form, that doesn't work, right? Because you got this thing happening, right? You're still removing heat, but the temperature is not changing. Well, that's the enthalpy is going on, right? So let's modify the temperature equation, which is all about a heat balance, right? To be, it's the enthalpy that's changing due to heat flux and volumetric heating. Right? Okay, well, that's all fine, right? But this is an equation with two unknowns in it, so you gotta tell me some relationship between E and U. Well, okay, you got two choices, right? You can write E as a function of U, except already you can see that that won't work, because when U is equal to 0, E could be anywhere between 0 and 1, right? So you got to go with the other one, right? You got to write U as a function of E. So to proceed, we need an expression for U as a function of E. Okay, and I'm going to look at this thought experiment picture, and I'm going to see pretty clearly this is E if E is less than 0. It's 0 for E between 0 and 1. And it's linearly increasing, but with an offset for E bigger than 1. And of course, you could, the enthalpy is only determined up to a constant. You could shift this whole thing around if you wanted to. So now we have E of t is U of E xx plus f of x and t, right? And of course, you notice there's some discontinuities in the derivatives of this function, which are going to do some interesting things here, right? We can say that this is going to give us weak solutions, right? But we're pretty okay with the idea of weak solutions, hopefully, at this point. Okay, and well, so that's the formulation, right? You're going to get E out of this, right? And then from this, you can post-process what region you're in, right? If you want to look at the ice fraction, I think I messed it up again. Phi is equal to 1 is pure ice. Okay, so I may have messed this up in the notes. I've messed it up here, right? So when E is negative, I am pure ice. Yeah, so this is wrong in the notes. When E is bigger than 1, I am pure water, so no ice. And then I go from 1 to 0 if E is in here. So it's incorrect in the notes. My apologies. You know, I'm just trying to think. Yeah, there's another application I'm looking at. Actually, it's a collaborative research project on sea ice formation, where I have the phi going the other way. So that's why I'm getting confused. Okay. That's not a Math 400 topic, that one. That's too complicated. Okay, so you got this. You're going to expect weak solutions from this, since U of E is continuous, but U prime of E is not. But this gives sensible solutions. come from volumetric heating or cooling to mushy regions formation and transition to regions of pure ice or water. And there's a capturing computational method based on this formulation. And remember what I talked about capturing methods, right? This thing in here doesn't look at like where the interfaces are, right? Right? It's just something that as you compute, you'll figure out whether E is less than 0 or bigger than 1. And that will tell you the regions of the pure things, and where you have this transition is where you will get the boundaries between the different regions. Now, I want to say, and I'm going to hand wave, okay, right? Because this is not a course in computational methods. We're not going to implement this, right? Although it'd be great to do in Math 406, which I'm teaching next fall. If any of you are brave enough to take that with me, we could do some enthalpy method computations and watch our mushy regions form and our ice move back and forth. Let me just say this formulation can also handle our original Stefan problem. Right? So remember, the Stefan problem was, well, I had water. And then I have a sharp transition to ice. Right? So in fact, when I try and put this thing in, right, I'm going to have discontinuities in E, which will come out, discontinuities of E in time. But remember, the Stefan problem has a discontinuity in the derivatives of U. This equation, if you interpret it the right way, can handle those discontinuities as an appropriate weak solution, which is exactly the Stefan problem with this sharp interface between them. So I'm hand waving a little bit, but sometimes you need, with free boundary value problems, you need to track, right? There's no way around it. But when you can have a capturing method, all sorts of things fall into place that are advantageous. There's a question coming in. Why don't we expect a mushy region in the Stefan problem? That's an excellent question. Remember, I think it comes down to a maximum principle, argument, right? Like we're getting away from the maximum principle because we don't just have the heat equation, right? We got this F, right? So if this F is 0, right, that means you have to have U positive on one side and U negative on the other side of the 0 thing, right? If it's positive on both sides, right, then it's all water, or if it's all negative, it's all ice, and so there is no Stefan problem. So once you don't have this forcing term, right, then you're really saying you can't have mushy regions, right? Because you gotta have positive on one side, negative on the other side, temperature. Okay. It is interesting the difference in behavior you get between boundary forcing and interior forcing. Maybe I haven't quite explained it perfectly, but at least you understand there's a phenomenological difference between those cases. Oh, there's a question that came up. Can you explain what a capturing method is? Again, so this is not a computational course, but you know, we are talking about looking at a PDE problem and looking at different formulations of it to figure out which formulations might be suitable for numerical approximation. So in that sense, let me follow this a little bit more. Let me highlight the difference between a tracking method and a capturing method. So we're looking at free boundary value problems, right? So a tracking method would say, well, let's just look at 1D, okay? Tracking method would say, I'm going to actually have S of t as an unknown, right? And I'm gonna, like, ds by dt, right, is this jump in du dn, right? I'm going to actually implement this. And then how you would do it, right, is you'd have some grid points over here and some grid points over here. And as S, you know, moved in time, you would let these grid points like stretch out as S moved to the right. And these grid points compress as F in the same scenario, right? So you'd have some approximation in the ice region, some approximation in the water region, and you would be looking at exactly where S is. Capturing method is different. So now we're going to look at this enthalpy method. Right? So in the enthalpy method, what you're going to do is you're just going to have a grid. Right? You're going to compute the enthalpy on the grid points. Right? And then you can look at the enthalpy and it will tell you afterwards, like, as the enthalpy went from 0 to 1, in between those grid points, that's where the interface is, but you're not, there's no S of t that you're keeping track of here. You're just keeping track of E and looking at it to figure out where the interface is approximately. Does that answer your question? Okay, yes, says Julie. Okay, good. Well, now there's other free boundary value problems. let's look at some of those. I happen to be interested in this one. This is a pretty simple one. And let me talk about the difference. So let's think of the Stefan problem. This was an example of an explicit boundary value or free boundary problem. Or moving boundary value problem. Why explicit? Well, because I had the velocity was like given. So let me show you an implicit free boundary value problem. Okay, and in this one, there is an extra condition. At the free boundary. That determines the motion implicitly. Okay, and there's the one-sided Stefan problem is the simplest explicit free boundary value problem. And there's a simplest implicit one-sided free boundary value problem. It's called the oxygen depletion problem. Okay, and I'm going to just write down the scaled version of it now. So I'm going to have an X, and this is going to be a depth into living tissue. It's a math biology or a medical physics application. At X equals 0, I'm going to have a capillary. So there's some blood flow out here, which has got oxygen in it. And I'm going to have a flux of oxygen into this tissue, right? So this F, I put the sign so the F positive means flux into the tissue, which I guess I like. So this is flux of oxygen in. And then the problem is going to be for U of X and T. This is going to be the scaled oxygen concentration. Right, and the oxygen will diffuse. I've scaled it so it's got diffusion coefficient 1, and it will be consumed. Right, and I'm going to give some initial conditions. If that's all there was, we'd be back to old news in the course, right? Okay, but now we've got a constraint, okay? The tissue can only consume oxygen if there is any there, right? So U is constrained to be bigger than or equal to 0, right? So I'm going to have my Ux is minus F. I'm going to be pumping some oxygen in, okay? And I'm going to have a free boundary. Here's where the free boundary is, to where these poor guys are oxygen starved. The oxygen is depleted out here. Okay, so there you go. U is identically equal to 0 outside of here. And then in here, I'm going to have U of X and T being positive, and I'll have a shape something like this. Right. Well, this is going to be, this F could depend on time. So this shape is going to move around. And what? I need some conditions here, right? I've got that UT is UXX minus 1. I've got a boundary condition for the heat equation on one side. I need a boundary condition for the heat equation on this side as well. But if you count, remember I'm a counter. I told you the story of my buddy that mocks me still. In fact, he mocked me just the other day about how I count conditions. Well, you need two conditions here, right? Because you need one to match up with this parabolic PDE, which needs a boundary condition on the right-hand side. And you also need an extra condition to determine what's happening with S. Now, if this was an explicit free boundary value problem, then you would be given the velocity in terms of U or its derivatives, right? But that's not what happens here. So here, if you look at the conditions at that free boundary, well, clearly, like that one's pretty obvious, right? Okay, so you're going to have nothing going on there. This one is obvious if you think about it a little bit. The boundary has to meet with a 0 derivative. So now I got my count is right. I got my two conditions that I need here. One is for U and one is for S. Okay, it's not clear. Like it's not like one is for U and one is for S. It's like there's two, you know, for U and S. I've got one boundary condition for U, the other implicitly determines S of T. Okay, I got 5 minutes. Okay, so I'm going to go on and do a few other things next week, but let's do an easy example. This is the sort of example I'm going to get you to do for some of the other free boundary value problems that we have looked at, or we will look at, or maybe some new ones. The sort of thing that you can do in a Math 400 question are, you know, things that you can do with pencil and paper, and an easy one is determining a steady state. So let's determine the steady state solution, right? I've got this heat equation, right? So I know the effect of initial conditions is going to die away. I will get a steady state. I mean, there's the free boundary problem aspect to it, so maybe you're a little bit worried, but you will definitely find a steady state, and it has the property that solutions will tend to it. U of X when F is equal to 1. Right, so I'm going to have U double prime. I'm going to have the equation without time dependence. This is a real steady state, not one of our time harmonic limiting solutions. It really won't depend on time. So I'm going to have U double prime minus 1 is equal to 0. That gives U is 1/2 x squared plus some unknown coefficients in front of the integration constants. And I know that u prime at 0 is -1. So that tells me that b is -1. And now you think about it and you go, well, now I only have a to work out, but I've got two conditions. Well, but you have to work out what s is as well. So now work out a and s with the two conditions here. I know that u at s has to be 0. That tells me that 1/2 s squared plus a minus s is equal to 0. And I know that the derivative has to be 0 here. That's another condition. That tells me that s minus 1 is equal to 0, right? So I get s equals 1. And if I go back there, I get a is 1/2. And I get u of x is 1/2 x minus 1 squared. There's a classic problem in the literature, which is to start off with this solution. So this is, you know, oxygen in tissue. So this tissue is not active, right? You get some active tissue down to some depth. And then start with that as initial conditions and switch to f is equal to 0. So you're depleting the oxygen. You're not giving it any more oxygen. And in that case, this S of t moves this way. And because of the -1 term, everything decreases. And this S of t goes to 0 in finite time. So this is the problem that people have been interested in the past. And there's just to continue the tracking, capturing discussion. There's tracking methods and capturing methods for this problem and other implicit free boundary value problems. I got a little bit more that I'll talk about this next time. And then we'll go on to the Black-Scholes equations from mathematical finance, mathematical economics. It's another free boundary value problem, which we'll have a look at. Okay, that takes us to the end of the lecture. I'm going to stop recording, but I'll stick around for the usual